Steinhauer here. Welcome back. We are ready to get down to the nitty-gritty of nuclear fusion in the sun. We know we're going to take 4 hydrogen atoms to make 1 helium atom, but what are the specific set of steps that happen to make that actually happen in the center of the sun? So the specific set of steps is called, in the center of the sun, that happens most often, the proton-proton chain. So there are 3 steps. Let's go through them one at a time. The first thing that happens, you've got a bare proton and you've got another bare proton, and you smash them together hard enough, nuclear physics happens, and out the other end comes an atom that has 1 proton and 1 neutron. Okay, so if we are writing this down in equation style, so this is pictorial style, equation style, you will say each one of these is a hydrogen atom, because all hydrogen atoms have 1 proton in the nucleus, and this has just a bare proton. So these are both hydrogen 1s. Recall, hydrogen defines the element, meaning there's only 1 proton in the nucleus, and the 1 is the total number of nucleons in the nucleus, in this case 1, right? So continuing, we have 2 of those, H1 plus H1, and that goes to an atom that has a single proton and a single neutron in the nucleus. This is still a hydrogen atom. It's just a hydrogen 2 atom. Still hydrogen because it has a single proton in the nucleus, but it's a hydrogen atom with a neutron also, so that is H2. So there's, you may know, you probably don't know, but you may know that there's another name for the H2 nucleus. Sometimes people will call this deuterium, or a single H2 nucleus, a deuteron. But that's just a fancy name of saying an atom with 1 proton and 1 neutron. Now, with these reactions, you actually have to obey some laws of physics. Laws of physics require a couple of things, and you have to, it's sort of like an accounting ledger. Whatever's on one side, you have to have the same things on the other side. So, and there's several of these rules that have to happen. First rule is, you can't have different number of nucleons on one side as the other. So nucleons, by nucleons, I just mean protons and neutrons. So we've got 2 protons on the left, two nucleons on the left, and 2 nucleons on the right, so that we can check off as we have successfully satisfied our conservation of nucleon requirement. Another requirement, though, is conservation of charge. If you start off with a certain number of charge in the beginning, after the process ends, you have to have the same amount of charge on the other side. And that we have not done a good job with yet. We have 2 protons on the left and a single proton on the right. On the left, we have a net +2 charge. On the right, we have a net +1 charge. So this reaction won't work yet as we have given it here. You need something else coming out in this reaction that also has a net positive charge. And that thing is called we're going to give it the symbol E+, and it is called a positron. A positron is interesting. It is an antimatter particle. It is, in fact, an anti-electron. Most elementary particles have antiparticles. So, for instance, the positron is the antiparticle of the electron. The antiparticle has all of the exact same characteristics as its regular particle, except it has the opposite charge. So an electron has exactly the same, a positron has exactly the same mass as an electron, and lots of other characteristics that you could talk about, but it has, instead of a net -1 charge, a net +1 charge. And so here is the other positive charge that's coming out on the other side. So now that we've added this positron, our charge conservation is all set. Now it turns out that the positron, though, has something else called a lepton number. It doesn't matter what leptons are, but since there are no leptons on this side, and the positron actually has a net negative lepton number, we need something else to come out to cancel out the now non-zero lepton number that we've got on the right. And that other thing, it turns out, is a neutrino, which I'm going to designate with a Greek letter nu, lowercase, and this is neutrino. And a neutrino, the trino is literally Italian for little neutral one. Very, very low mass, neutral in charge, which is good because we can't have any more charge now that we've got that evened out. But it's got a positive lepton number that cancels out a negative lepton number of the positron and gives us a net zero on both sides. So this is the entire first stage of the proton-proton chain. You've got the H2, which gives you both of your nucleons. You've got the positron, which gives you charge conservation. And then you've got this neutrino coming out, which gives you lepton conservation. Now, what's going to happen to this positron and this neutrino? Well, you need to know something about antimatter. And that is that when an antimatter particle encounters its regular matter cousin, they immediately annihilate one another and turn themselves into energy. And so this electron that gets emitted, this positron that gets emitted, will almost immediately encounter an electron because there's free electrons flying around all over the place in the center of the sun. And so it will very quickly go away and be converted just into energy, high energy gamma photons. Now, the neutrino is a very interesting object, and we'll talk a little bit more about it later. But the neutrino is a particle that interacts only via the weak force, which is the fourth of the four fundamental charges I mentioned before. You've got gravity, you've got electric force, and you've got the strong nuclear force holding atoms together. The weak nuclear force you need to understand to be able to understand some reactions like this, but isn't all that important in most everyday life. But this neutrino only interacts by that weak nuclear force. And it's called weak for a reason because it's a very weak force. And so it turns out that most neutrinos that are generated in the surface of the sun come streaming right out of the sun, at the center of the sun rather, come streaming right out of the sun without even noticing that the rest of the sun is there. They interact extremely weakly with matter. So the positron has gone instantaneously because it interacts with the first electron it sees. The neutrinos come flying out virtually untouched because the neutrinos just don't see anything else. They just keep going. Okay, so that's the first step of the proton-proton chain. We've turned two hydrogen atoms into a deuterium, H2 nucleus, plus we've emitted a positron and we've emitted a neutrino. Great. What is step 2 of the proton-proton chain? Well, step 2 is, let's take one of those deuterium nuclei that we just created, and let's smash that with another proton. Bring these two together, nuclear physics happens, and out the other side comes a nucleus that has 2 protons and 1 neutron. Okay, so let's write the equation form of this. We've got a deuterium nucleus, that's an H2. We're adding another proton, that's an H1. This goes to an atom that has 2 protons and 1 neutron. This is no longer a hydrogen atom. If you go and look at your periodic table, the element that has atomic number 2 is helium. So this is a helium nucleus. All helium nuclei have 2 protons in the nucleus, and specifically, it's a helium-3 nucleus because there's 3 total nucleons in the nucleus of this particular atom. So we have successfully done nucleon conservation. We've got 3 at the beginning and 3 at the end. Have we done charge conservation? We have actually. we have +2 at the beginning and +2 at the end. So we don't have any other, we don't have any positrons or anything else coming out of this reaction. The thing that does usually typically come out of this is a gamma ray photon. And I'll put that as a gamma. That is the Greek letter gamma. And this is a gamma ray, which is just a high energy photon, if you remember your electromagnetic spectrum. So I'll say plus gamma down here. Photons though are chargeless, they're massless, they carry away energy, but they don't contribute any lepton numbers or anything else. In fact, they help you with a particle with a conservation called spin and angular momentum. But that's totally beside the point. Mostly, we're just interested in what's going on with the nucleons. So that's important. Okay, we're almost there. We've made helium, but we haven't quite made helium-4. And helium-4 is where it really becomes advantageous to get to, because that's where matter wants to be. It's a very low energy state, which is where atoms want to be. So we have one more step to get to helium-4. And that step usually is taking one of these helium-3 nuclei that we've just made, and another one of these helium-3 nuclei that we've just made, smashing them together, nuclear physics happens, and out the other side comes an atom that has 2 protons and 2 neutrons. In equation form, this is He3 plus He3 goes to, what element is this? Well, it's still helium. There's still 2 protons in the nucleus, but it's not helium-4, that's not helium-3, it is, in fact, helium-4, since there are 4 nucleons now in the nucleus. Now, have we satisfied nucleon conservation? No, we have not. So we're not done yet. What usually also comes out, we also haven't done charge conservation, because we started off +4 and we ended up +2. So we need 2 other things to come out. And those 2 other things are 2 more bare protons. So we have 2 hydrogen 1s also being released in this particular reaction. And now we have nucleon number, start with 6, end with 6, and we've got charge conservation, start with +4, end with +4. So our cosmic ledger sheet is balanced. And these 2 protons are now free to start this process all over again, combined together at some point then to begin the process over again. But the other thing I want to point out is that you need to do the first 2 steps twice to be able to do this 3rd step, because you need 2 helium-3 nuclei, and those are only made by running through those first 2 steps twice. So really you need step 1 and 2 twice, and then you can do a step 3 to get your helium-4 nucleus and your 2 protons out. So here is the overall reaction. The overall reaction is you put in 4 protons, and since you had to go through steps 1 and 2 twice, you get out 2 neutrinos and 2 positrons and 2 of these gamma rays. The neutrino and positron from step 1, the gamma ray from step 2, and that gives you a nucleus that has 2 protons and 2 neutrons, a helium-4 nucleus. Now, there's 2 other things. You actually needed 6 protons altogether, but you get those 2 of those protons back. So the net reaction is you've taken 4 protons in, and you've gotten out a helium-4 nucleus, 2 gamma rays, 2 positrons, and 2 neutrinos. Okay, that's the gist of how that process rate plays out. In the next video, we'll talk about why that gives us energy. See you there.